Okay, so welcome everyone to today's lecture. My apologies for not being there in person because of a health situation in my family, but let's do it on Zoom. Okay, so let's dive straight in. So, so what have we learned so far? Just a quick recollection. We have had an introduction to deep learning, and then for the last several lectures, Ben has been teaching you about physics-informed neural networks, or PINs, for solving PDEs. And what he has done is that he has taught you algorithms. He has also taught you what are the various successes of these algorithms, as well as a few limitations, right? So this has been the content so far. And in today's lecture, and also in the lecture next week, sort of the main focus would be somehow to find out some insights, particularly some theoretical insights into why pins work and particularly why they don't work. So as you saw, there were several limitations of these methods. Why do these limitations come off? And what can we do to solve it? So that would be the main content of today's lecture and a bit of the lecture next week. So let's get started. Just to sort of recapitulate what pins are and to introduce a bit of the notation, because since we're going to do a little bit of theory, I have to be more precise with my notation and also more sparse in some sense than what Ben was. So first of all, so let's focus today on the forward problem for the PDE. So as you all know, pins can also be used in the context of inverse problems, but I think for the perspective of this lecture, let's focus on forward problems. And then the target is to approximate the solutions of this abstract PDE. So this is an abstract PDE, as abstract as it gets, because we are writing everything in terms of a differential operator, D, and in terms of input F, and in terms of the PDE solution U, right? So where are these objects defined? So in particular, because our inputs, so let me, as I said, our input as well as our solution, so U is the PDE solution. These objects are both functions, right? So they have to live in some function spaces. So we say that the input lives in a function space Y. This could just be some LP space. So LP simply means P integrable functions. So L1 would be integrable functions, L2 would be square integrable functions, and so on. And similarly, U, the solution, this lives in the space X, which is another function space. Okay, and these function spaces, they are defined on a domain. So this domain could be an open set in space, or it could be open set in space-time, depending on whether the PDE that we are having is a steady state PDE or whether it's a time-dependent PDE. So this is sort of the basic setup. And so we have an input to the PDE and we have an output to the PDE. So this is F is the input, U is the output. And what links them together is the differential operator, right? This is a PDE has to have an underlying differential operator. And this differential operator is the one which takes the input, which sits in the space X, and goes all the way to the output, which sits in the space Y, right? So this is sort of the basic setup. And this is, let's say that this spaces X and Y are defined such that this differential operator is well defined. So now you can ask me, where are the boundary conditions, where are the initial conditions? So because for time-dependent PDEs, we need an initial condition, and for all PDEs, we need boundary conditions. So what I've done is, just to keep notation simple and straightforward, these conditions are actually implicit. So in the sense that they are already included in the input F, okay? So when you have the input F, you have the initial conditions and the boundary conditions that are included. And as a concrete example, we always look at the heat equation. So this is a heat equation in several space dimensions. So in this case, the differential operator D here is given in terms of the time derivative, the partial derivative with respect to time, and the Laplacian with respect to space. And remember that the Laplacian of D, U is nothing but the summation J from 1 to D of U xj xj. So you take all the second derivatives, the second derivative matrix, it's called the Hessian, and you just take the trace, and then you'll get the Laplacian. So this is a concrete example. So you take a function U, you apply the differential operator, the heat equation, the heat operator, which is given here, and then you get the input. So the task of solving the PDE is given this input F and the differential operator D. we have to find the solution u. So this is a very, very straightforward setup that you can imagine. And then how do we work with pins? How are pins going to solve it? So if you remember, the first ingredient of pins, of course, without saying much, are deep neural networks. Again, I need some notation because this is sort of my notation. So as you can imagine, we have a mapping which takes some input, in this case, y, if you remember. So D is the domain now. So this sort of calligraphic D is the domain. And this could, depending on the context, be just a subset of space or of space-time. And this Y now, I didn't write it, but this Y belongs to this calligraphic D. Okay, so these are the coordinates, space and time coordinates. And then the deep neural network, U star, is defined in terms of all these layers that you know very well. Each layer has two elements to it. The first one is this affine piece, given in terms of a weight matrix W and a bias vector B, BK and WK for the kth layer. And then you also have an activation function, a scalar activation function. And because we are going to differentiate sometimes many times, our activation function is typically a sigmoid or a hyperbolic tangent or something smooth, not ReLU, which has potential discontinuities in its derivatives. And the parameters, so this is just a neural network that defines, ultimately goes into the pin algorithm. And the parameters, the free parameters that we are going to tune are the weight matrices WK and the bias vectors BK. So this is sort of the basic setup, standard plain vanilla deep neural networks. You have seen several examples of them also in the tutorials. Now, what we do with pins is that we take these deep neural networks. We know what the inputs are. We also know what the differential operator is. And we are going to approximate the solution here, U, with deep neural networks, right? So this is the basic objective, the basic algorithm. So as I said, means each of these neural networks are defined in terms of this parameter vector theta. And this parameter vector theta is now given by, so it's here. And this defines the deep neural network, U theta. And this is what is going to approximate my solution of the PDE. I don't know why there is a star here. Let's say that it also belongs to X, or we could say that this was a subset of X. Okay, good. So now objective here is that we know that there is a solution to the PDE, which we don't know what it is. We are going to find the theta such that this guy approximates this U, and it approximates it in a suitable sense. And what is the sense in which it approximates is what we are going to talk about today. But the way in which it does this approximation is, it doesn't have any labels, right? It does not have access to, necessarily have access to values of U. All that it has to do is to work with the inputs, which are given by this F here, and by the differential operator, because we know what the differential operator is. So recalling, what you do is that you compute the PDE residual. So PDE residual, remember that the PDE is simply D of U equals F, right? So now you just apply, instead of U, you apply this differential operator to U theta and take the difference here. Of course, this is not going to be zero, because if we are lucky and it's zero, then the problem is solved without any error. But in general, it will lead to what is called a residual. This is the residual with respect to theta. And we can compute this residual, as I said, by automatic differentiation in general. But also, I think Ben told you that sometimes you can also use finite differences. But let's say from our perspective, we'll just use automatic differentiation. So now, at every point, in principle, we can compute the residual of the PDE for a given neural network. But of course, it doesn't help to be able to compute it at every point, because at the end of the day, we have to take some sort of an integral, some sort of a global quantity, right? Because point-wise quantities, they're not really useful. So what we are going to do is that we are going to take the LP norm here of the residual. So we integrate it across the domain. We take an average in some sense. And usually the P is equal to 1 or 2. So these are the two common spaces, although sometimes you might need something else, okay? But for the time being, let's say that these are 1 or 2. So now the objective is you find a theta such that this residual is going to be minimized. But of course, this is an integral, and you can't just compute integrals by hand. So what you have to do is to replace this integral here by a quadrature, Okay, now this is sort of standard in numerical analysis. You replace the integral by a quadrature, and to do so, you just choose some. So you have a domain here, D. This is your domain. You throw some quadrature points in it. This could be random points, okay? Usually the simplest is to take random points, but that's not necessarily the best. So there has to be a quadrature rule. There are some quadrature weights here, and you replace this integral out here with this quantity here. So this is a quadrature. This is an approximation of the integral. And then you take a theta star, you just minimize this, right? So this is the loss function now. This is often called the physics-informed loss, because there is no supervision here except for the initial and boundary conditions, which we have said are implicit. So you have some physics-informed loss. And now you just, this is of course, as always in machine learning, this is a high dimensional non-convex problem, very high dimensional non-convex problem. And we are going to use some stochastic gradient descent, right? So this is the PINS algorithm, that you take a class of neural networks, you compute the residual in terms pointwise by using automatic differentiation, and then use a quadrature to approximate some global quantities, minimize, and you're done. So this is the algorithm. And I think Ben has explained this algorithm, shown many examples of this. And you could say that in some sense it works. So, I mean, this is a question, does it work? So for instance, some sense it does work. So here is the multi-D heat equation. Remember, this is UT minus Laplacian of t u equal to 0. So this is the multi-D heat equation. Now D here changes all the way from 1 to 100. So this is a very high dimensional PDE. You will see later why we care about that. And then we fix the pin here, the neural network, with it's just 4 layers. So you have four layers, 20 neurons in each layer, not at all a big neural network. And then we need quite a few quadrature points because we have so many dimensions. And then we try to do this approximation procedure, right? So this can be done. And all the points here, so these interior points and boundary points, these are sort of random points, because in very high dimensions, nothing else works, right? You just have to take random points. And when you do that, then you see that for the same network somehow, and for the same amount of training time, you'll see that there is an increase in error. It's of course very, very small for very small dimensions. And as you go up in dimensions, the error does increase, but it's not increasing exponentially or anything. If you see now from going from 20 to 50, it is roughly doubling, which is what you would expect. And then from 50 to 100, it's also less than doubling. So you would say that this is a linear increase, which is the minimum. So in some sense, it does not have what is called a curse of dimensionality. Curse of dimensionality would be, for instance, if you would have an exponential increase. Right here, this is not at all the case. So at least for this simple example, where the complexity comes from the fact that you have lots of dimensions, because in general, you can't solve the heat equation in 100 dimensions using the finite difference methods that I taught you in one of the lectures. So it somehow works, right? But then you have also seen other examples where it doesn't work. So how do we know when it works, when it doesn't work, why does it work, why doesn't it work, and so on? So this will be the focus of the next couple of lectures. So let us get started. Of course, if you have any questions, you can always ask me in the chat button. Okay, this is always possible from time to time, or you can raise your hands if you're so inclined. So either of the options is there. We can still make it interactive even if we're all on Zoom. Nevertheless, let's go ahead and let's try to address this question, right? Why do they work sometimes and why don't they work sometimes? Okay, so then again, I go back to the abstract PDE because then the notation becomes very, very light and you sort of see the abstract structures, the mathematical reasons why things may or may not work. So this is the PDE, du equals f. And remember that my pin solution is u theta, right? So this is the u theta. This is what the PINS algorithm gives me. And the objective, always in this problem, there is a very, very specific objective, which is that you have to minimize the total error, right? So the error is between u, which is the exact solution, which we don't know it, but it is there. And u theta is the approximation that we obtain with the algorithm that I just described to you, right? So this is sort of the objective. So now the question is that, so this is what we want to minimize. We want to make this as small as possible, right? Depending on the accuracy. So in engineering, for instance, it's usually around 1%. So a couple of digits, 3 digits. In some other applications, it could be more. In some other applications, it could be less. Now, what contrasts spins from what is standard supervised learning is that we don't, or we may not have, in general, we don't have access to samples from the exact solution. So we have no control. We are never training the network directly on this error. Because in, let's say, in regression or classification, traditional use of machine learning in images or text, what you do is that you have some labels, and then you have the predictions of your network, and then you try to make the distance between them as small as possible. Here, we don't have access to that, right? That's why it's a fully unsupervised approach. However, so what we do here is, if you remember, we are working with the PDE residual, which we are, of course, taking some norm on it, some LP norm. Yeah, so this is the LP norm, you see, so that you take the pth power and you take a 1 over p. So just think of p equal to 2 would be like the root mean squared error. And p equal to 1 would be the mean absolute error. Many of you might have seen these objects. Okay, so now this is what we try to minimize. What we have some access to are these residuals, and I denote this by EG. Sometimes people call this as generalization error. But think of it as the PDE residual, because you don't have access to this. This is not even your target. You don't try to make it small. What you try to make small is this mismatch here. How much of a mismatch does it have at the level of the PDE? And in fact, in practice, you don't have access to this guy here. What you have access to is the training error, right? So the training error is nothing but a pth root of the loss function. Because if you remember, this is my loss function. So the idea is that by minimizing or making the loss function as small as possible, can I somehow go back, make this small, make the total residual small, and eventually from here, can I go back and make the total error small? So let us try to sort of put these questions together. And this is what I have done as somehow the key theoretical questions. The first thing is, and this is very important in some sense, is that we are not searching for a vacuum. You're not searching for a vacuous statement. What do I mean by that? So remember that my objective, or in some sense, my objective is to make the training error as small as possible. And underlying why I want to make the training error as small as possible is because it's, after all, a discretized version of the residual. So I want to make the residual as small as possible. So the question is, can this even be done? Means otherwise, what are we doing, right? So in other words, do there exist parameters, in this class of neural networks such that, let's say, the training error can be made as small as possible and the PDE residual made as small as possible? Because if these errors are not going to be, or these objects are not going to be as small as possible, there is no point in doing anything. Let's say that this epsilon is like 100, then what is the order of the error will always be of the order of 100, right? So it does not really help. So in other words, what kind of neural networks can we take such that these quantities, at least a priori, can be made as small as possible in principle? In practice, whether this happens or not is another question, and we will see that. So that's the first question that we have to ask. Is this even a feasible problem in some sense? Can we even address the feasibility? Then, of course, as I said, means in practice, we don't have access to this error. We only have access to this error here, the residual. So it's natural to ask, if I make the residual as small as possible, does it automatically imply that my total error, the object that I want to make as small as possible, can that be made as small as possible? Of course, trivially, this is true if we have a bound which looks like this. It tells us that the total error, the object that we want to minimize, is bounded in terms of some constant times the PDE residual. So making the PDE residual small will automatically imply making this, will automatically make this object small, right? So this will somehow justify why we are going to try and make this residual as small as possible. But we never have access to this quantity, because remember that this quantity here is an integral, right? So we don't have access to this quantity. we always have access to it through its discretization, through this training error. So then we have to go one step further and say that if you have a small training loss, because that's the only thing that we can read out during our algorithm, if you have a small enough training loss, does it automatically imply that the residual is small? If it is so, or in other words, if it is so, then, or this will be true if you have a bound which looks like this. So this tells us that as long as the number of n is the number of quadrature points, so n is the number of quadrature points. So what does this tell us? This tells us that as long as you can make the training loss small and the number of quadrature points as large as you want, then the total means somehow this generalization error can be as small as possible. This residual can be as small as possible. And from here, you can go back to the total error and make it as small as possible. So this is sort of the, let's say, the hierarchy of questions that we have. So let me recapitulate. So what we want to do is first, can we make the training error as small as possible? And then once we have small enough training error and large number of quadrature points, does it automatically imply that there's a small residual? And does a small residual automatically imply that the total error is small? So that's the mechanism through which pins can work, right? Otherwise, how else can we connect the training error to the total error, which is, these are completely different quantities. They're sitting in different spaces. They have different meanings. So the only way we can do this is through this route. At least one way in which we can do this is through this route. Now, let me try to explain this a little bit more in detail so that you don't get lost, right? So actually, this is not that, let's say, it looks a bit abstract, but it's not that unrealistic to, or not illogical to expect this, if you know what I mean. So let me start by the first question here. The first question is, are we even solving a feasible problem in some sense? In other words, can the total error and the training error be made as small as possible? And the answer to that actually is yes, because this depends on the PDE residual. This depends on the smallness of the training error. So how can you do that? So the answer is here, because remember that at the end of the day, so let me use this. So we are solving a PDE, which is given by here. So now the PDE solution is, although it's not always the case, in many, many cases, is actually a smooth function. So just imagine that you have the heat equation. So the heat equation is having one time derivative and two space derivatives. So if the right-hand side is even an integrable function, the solution of the heat equation better have two space derivatives and one time derivative. So it's smoother than the F here, than the input here. Now, this is not always the case, as you will see in the next lecture, but often this is the case, that there exists the PDE solution is going to be smooth. Very good. So what does that imply? That implies that if you look at the pin residual, so the pin residual is here, this is defined like this. So you apply the neural network, you apply the differential operator on the neural network, take out the input. Now, what is the F here? F is nothing but D of U, right? So this is F is nothing but D of U. So I have simply substituted this here. So now we have the differential operator applied to U theta and the differential operator applied to U. And this gives us an estimate. Let me just for simplicity, let me try to take this and expand it out for the heat equation, for instance, so that you're not completely lost. So for the heat equation, if you remember, so let me take black here. So this is the object that I'm going to sort of expand, right? So I have d of u theta minus d of u, right? So d of u theta is nothing but dt, the partial derivative of u theta, minus Laplacian of u theta, minus dt of u, minus Laplacian of u, right? Let's put some norm here. So this is nothing but dt of u theta minus u, minus Laplacian of u theta minus u. Right? The differential operators are linear. So this is less than or equal to, by using triangle inequality, u theta minus u plus Laplacian of u theta minus u. Or in other words, this is nothing but, you can say, u theta minus u. And I don't want to sort of expand notation too much, but in what is called W1P. And Laplacian is a second derivative. So this is u theta minus u in what is W2P. One is in time and the other is in space. Okay, just very formally, I'm not doing the math. So W1P simply means that the function is close to something and its first derivative is close to something, to the first derivative of the same thing. Here it means that these two functions are close to each other, their first spatial derivatives are close to each other, and the second spatial derivatives are close to each other. So when I measure things in this spaces WSP, it means that I'm demanding that not only are two functions close to each other, but also the derivatives, the second derivatives, the third derivatives, fourth derivatives, and so on are also close to each other. And this S here, as you can see, clearly depends on this differential operator D. If we have more derivatives, then we are going to have more of this object there. Good. So this was essentially the content of what I wanted to say. So for a nonlinear PDE, of course, as you can imagine, this was a linear PDE. So there everything sort of worked out. But for a nonlinear PDE, it's slightly more complicated. And you get some things, some constants, which depend on the function itself. That's why it's nonlinear, right? Otherwise, it would be a linear PDE. But essentially what it says is that the PDE residual can be estimated in terms of the difference between the exact solution, the function, and the neural network measured with the right number of derivatives. So that's all is there to this mathematical derivation. So all that we need to guarantee, so to guarantee that the PDE residual is going to be small, all that we need is to guarantee that there are neural networks which are going to approximate the PDE solution, which is a smooth function, with sufficient number of derivatives, right? That's all that you do. Now, this is where already I think Ben has introduced what is called a universal approximation theorem. So what is a universal approximation theorem? It's a very important statement for neural networks. It's one of the reasons why people believe neural networks work so well, which is that if you take any function, means this u is, as long as it's a continuous function or even an integrable function, then there always exists a neural network, even a shallow neural network, which is going to approximate it in the right norm as to as much of a tolerance as accurately as possible. So this is the advantage of neural networks, that you think of any function. You see, any function, it just needs to be integrable. In fact, it needs to be what is called measurable. There always exists a neural network which is very close to it, right? So this is sort of the basis of neural networks. Now we are invoking a similar kind of a question, except that we want not just the function to be close to another function, but also its derivative should be close to the derivative of the function, its second derivative should be close to the second derivative of the function, and so on. And there are similar theorems, for instance, one of my own theorems, which say this, that this indeed can be done, that you can always find neural networks which not only approximate a function in an integrable sense, in an average sense, but also approximate the derivatives, the second derivatives, the third derivatives, and so on. So because the solutions of the PDE are in some sense smooth, this automatically implies, and because neural networks are universal, they can approximate any function, it automatically means that there exists neural networks such that the pin residual is going to be small, okay? Which is what we wanted to, right? We wanted this pin residual to be as small as possible so that we are not solving a vacuous problem. And the same argument also works for the training error. Because what is the training error after all? The training error just takes the, if you remember, I have it somewhere, yeah. So the training error is simply that it takes this integral and it approximates it by a quadrature, right? So this is traditional numerical analysis. How do we take the integral of a function and just approximate it by some weighted combination of the function evaluated at points? So as long as the function is smooth, the underlying function is smooth, there are many, many different ways in which you can do it. Even if it is not smooth, you can use Monte Carlo or central limit theorem. So this tells us that if the pin residual is small, and if there are sufficient number of quadrature points, remember that we have smooth activations. So this is typically hyperbolic tangent. Then this works quite well. And this tells us that from this result, you can come to this result. So in other words, that the loss function or the training error, provided that there are sufficient number of points, can be made as small as possible. So you are not searching for some needle in a haystack. Probably, at least there is a needle somewhere. Means you're not searching for nothing in a haystack, So this tells us that these kind of arguments, what they tell us is that the problem that we're trying to solve is in some sense well posed or is feasible, that you can actually find neural networks such that this training error can be made as small as possible. And if you have sufficient number of quadrature points, this automatically implies that the total error is going to be as small as possible, okay? Or the residual is going to be as small as possible. So in some sense, these kind of simple arguments, of course, for each PDE, this has to be carried out by itself. You have to compute this kind of an estimate. You have to argue why this result is true and so on. But the roadmap is right here, and it's fairly straightforward. So that part is easy. That at least in terms of the well-posedness of the problem, it is a well-posed problem in the sense that there are neural networks which sort of minimize, or there are neural networks which can make the training error in principle as small as possible. Whether you find these neural networks when you start at a certain point and you use stochastic gradient descent, this is a different question altogether. And this is what we are going to address in the next lecture. Okay, so far so good. This tells us that it's a problem that we in principle can solve. But this is only good to know, right? Because in practice, we are not doing this. In practice, we are starting with something. We are trying to make the training error as small as possible. And from there, we want to conclude that the total error is going to be small. So we have to invert this pyramid, as it were. So how do you do that? So let me just explain. It's not very difficult at all. So this again goes to some papers that I wrote some years back where this argument was first made, but now, of course, many people have fine-tuned it and have improved it. These were the first rigorous results on why pins would work. Okay, so the idea is very simple. So remember that we have essentially, so this is essentially the slide that explains everything. And I think after that, I will probably conclude because I don't have that much of time. Probably have 10 minutes. Okay, good. So the idea is that now we know in principle that the error can be made as small as possible. The training error can be made as small as possible. But given a small training error, can we go the other way and can we conclude that the total error is going to be small? So this is done in 2 steps. In the first step, we are going to argue. So again, it goes back to this picture here. So this is done now, right? So let's use the green and say that this part is done, that there exists neural networks such that these errors can be small. So now the question that I'm asking is this one. So does it mean if I have a small pin residual, can I make the total error small? Or in other words, can I get a bound which looks like this? Okay, let us try to see whether this can be done. And here is a strategy to do it. It is based on a property that we call as coercivity. There is no universal notation, but this is the term that we used. What does coercivity mean? It's sort of a stability property of the PDE. So remember that this is a PDE. So PDE is nothing but associated with the PDE, as you'll see in a couple of lectures, there's something called a solution operator, which is, think of it as the inverse of the differential operator, because given an F, it will give you the U. Okay, so this is how the PDE works. So now the idea of this coercivity, so remember all the time, F is the input, right? So now let us consider another input which is close to this PDE. Or in other words, let us consider D U bar is equal to F bar. So remember that my original PDE is DU equal to F, and now I have DU bar equal to F bar. So the idea is I perturb F. So I have a F bar which is close to F. What happens to U and U bar, right? I mean, this is a question of stability. I change the inputs to the PDE a little bit. Does it also get reflected in how the solution behaves? And coercivity says yes, that is indeed the case. So this is precisely the question. So this is nothing but F bar. This is nothing but F. So it says that if your inputs are close to each other, the output of the PDE, so this is a stability of the inverse operator somehow, of the solution operator. the outputs of the PDE are going to be close to each other. And in general, this, of course, there are constants because these PDEs can be nonlinear. So this is like, well, let's say Lipschitz continuity. Roughly speaking, it's a continuity statement. It's a Lipschitz or a Holder continuous statement. So this is a stability statement. We call it coercivity because this is a property that the PDE can have. So remember that the bottom line here of this entire estimate that I wrote down is given small changes in the inputs to the PDE, the outputs to the PDE, which is which the PDE solution would also have very small or relatively small changes because, of course, this depends on the constants. Now, how can we convert this into bounds in terms of residuals? So remember, my objective, and this is very, very straightforward, but it requires a little bit of concentration. Let's try to have that concentration. So this is the definition of error. Error is nothing but neural network minus the exact solution in some norm. But remember that the PDE itself is du equals to f again and again. But what is the neural network doing? The neural network is solving du theta is equal to f plus the residual, right? This is because you always get this residual. So the neural network is solving, it's a perturbation. It's a perturbation of f, and the perturbation is precisely in terms of the residual. Now this can be small or big, we don't know that yet, but this is a perturbation. So remember, what does the stability say? So that the difference between the outputs is bounded in terms of the difference between the inputs. So these are the inputs, and du equal to f. So this is what it is. And du minus f is actually because it's a norm, this is this generalization error. This generalization error, EG, is nothing but the norm of the residual, rests in some norm. So that's it. So this tells us that if this quantity is going to be small, right? So this guy is going to be small. If this nonlinear terms, these constants are going to be bounded, automatically the exact solution is going to be small. And that solves our problem because what we say, by minimizing the residual, by making it as small as possible, we are saying that the object that is making this residual as small as possible is as close as we want to the exact solution of the PDE. Okay, so this is one, let's say, a sufficient condition. This is not a necessary condition, but it's a sufficient condition which tells us that a mechanism by which minimizing the residual is akin to sort of making or approximating the solution of the PDE is provided by this coercivity. So this is a mechanism by which you can convert the properties of the PDE into an error estimate for the pin, for instance, right? So this is, if this is true, we have to verify it for each different PDE, and this is far from easy, but that's how, in the next lecture, you'll see some concrete examples. And then, but this is not job done, right? Because in practice, we don't have access to this residual. We only have an access, at least the norm of the residual, we only have access to the quadrature, right? This is, where is it now? The quadrature, which is here. So we don't have access to the residual, we only have access to the quadrature. So, but this is, again, there is a relationship between them because this is numerical analysis. You have a function and you have its, you integrate the function exactly, or you integrate it approximately. So how close the error is. And this is essentially what is called a quadrature error. So this is done in traditional numerical analysis. For instance, if you use, let's say, just random points, this number is going to be a half, right? Because we know that if you have random points, central limit theorem tells us that you can approximate the integral of a function by just what is called the empirical sum or the pointwise sum, and the error is going to scale like the square root of the number of points. So the PDE residual is given in terms of the training error plus some constants. Of course, these constants, they don't depend on the PDE itself. They only depend on the regularity of the smoothness of this function here, of the neural network, and the number of quadrature points. So alpha is sort of the rate of convergence that I told you. So if you think of Monte Carlo, some random sampling, then this is going to be a half. So this is, and P is equal to 2, alpha is going to be equal to 1. So this is sort of the mechanism. So first, if we can make the training error small, maybe I have even a slide here. Yeah, so let's say that if I can make this error small, the training error small, and this is not going to be an easy task, So in the next lecture, you will see that this is a hard task. If I can make my training error as small as I want, and if this constant is going to be bounded, if I take as many quadrature points as I want, then the residual is going to be small. So to make the residual small, I need to train my neural network in such a manner that I have a small training error and I have sufficient number of quadrature points. Okay, that makes my residual. So this you should think is just the norm of the residual, right? Residual norm. And then by using the coercivity, this is the one that I have sketched out. What you can do is that you can say that the total error is going to be small. So again, you have to compute these constants here in some sense. Means, well, this completely depends on the properties of the PDE, as we will see in the next lecture. And the first line here gives you guarantees that at least the global minimum of this ET is going to be as small as you want. This is a loss function. You never reach global minima. This is because it's a non-convex function. But if you did, then the global minimum can be made as small as possible. So that there's a hope, but there's a possibility that this quantity can be made as small as possible. This quantity can be made as small as possible. And if you have the right kind of PDE, that can be converted into making the error as small as possible. Okay, so this is sort of the algorithm by which we can verify whether pins can work or not. At least one of this is, as I said, it's all sufficient conditions. It's not necessary conditions. So what we are going to do is in the next lecture, at least part of the next lecture, is to look at some examples to see whether it is feasible or not. But I keep on repeating, and this is important so that you get a sense for where we stand. So the way it will work is you do your training, right? When you train the neural networks, you can actually compute the training error explicitly because the loss function is given to us, and you take a square root of it or a pth root of it, and you get the training error. That tells us the quantum of this loss function here. And then if you have sufficient number of quadrature points, this tells us that we need sufficient number of quadrature points that will make the residual small. And then depending on the properties of the PDE, the total error is going to be small. So now you can also see that this arrangement can fail in many ways, right? For instance, it can fail if you are unable to train the network well. The training errors are going to be large. It can fail if you don't have sufficient number of quadrature points. If it can fail if the PDE itself does not have this coercivity property. It can fail if these constants are going to be very bad, and these constants are going to be very bad. So there are several kinds of failure modes here, and we'll also see some examples of that. So I think I have come to the end of my time today. And as I said, in the next lecture, we sort of work it out. When will the project be online? People are more interested in that than in the lectures. Soon is the answer. Soon, because some of you requested that we don't have a project deadline in the end of May because people have exams. So we had to sort of change the schedule. So now there will be no project deadlines at the end of May, right? Someone is saying something just because it is graded. Yeah, it's okay. I think soon means either today or tomorrow. I cannot guarantee that because the last time I looked, it was more or less ready, but I think it's either today or tomorrow. That's who is saying now? What does she want now? Can you give us a preliminary schedule for all the projects? Okay, this will be provided. Okay, I will tell the assistants to release that. But tentatively, I think we just moved things a bit, right? So now it's the PINS project will be issued today. Will be something towards the end of April, and there'll be something towards the middle of June. But the exact dates, I think they will provide. Okay, so in that case, let's meet in person and also on Zoom next week. Bye-bye.
I want to ask a question.
Yes, sure.
Regarding the quadrature bounds, Why do you mostly use quadrature bounds? Would there be other kind of approximations that we can use, or is the quadrature approximation the best one we can ever
Any
think about?
approximation is a quadrature, right? What is a quadrature? Quadrature is when you replace an integral, which is a continuous quantity, by some form of a sum, okay, which is a discrete quantity. So whether you use Monte Carlo, you just, if it's Monte Carlo, maybe I can just, so instead of, now of course my pen has stopped working. So if you have f of y dy, you're going to approximate it by 1 over m f of yi, I from 1 to m. So that would be Monte Carlo, of course, in a probabilistic sense, but all of this are quadrature to me. Quadrature is any way in which you take an integral and you approximate it discretely. So everything, whether it's Monte Carlo, quasi-Monte Carlo, means Gauss quadrature, Newton codes, all of them are included in the same ambit. Is that clear?
Okay. Yeah, it's perfect. Thank you so much.
Any further questions? No? So the recordings will be provided, and also the slides, if they have not already been put on, they will be put on pretty soon. Okay, bye-bye.